Hi there. Today we are going to do a relatively quick overview of um, finding, calculating, and interpreting confidence intervals for proportions. So that would be like a single sample, and also for the difference between two proportions. So like a two sample proportion um, confidence interval. So in the book, this is chapter 8.2 and 8.3. So let's start in with chapter 8.2, estimating a population proportion. And so here's our generic formula for a confidence interval. We always start at our point estimate, which is our statistic, plus or minus our critical value, times the standard deviation of that statistic. And keep in mind, the critical value is basically how far we want to go out. Like if we want a 95% confidence interval, remember we want to contain the middle 95% of our sampling distribution or our data. And so we know if our sampling distribution is normal, that's the hope that 95% of the distribution will be within two standard deviations of the mean, right? Like our 68, 95, 99.7 rule. So let's kind of briefly build or quickly build this formula, this specific formula. So now we're moving from like the theory into like the specific mechanics. How do we actually create and interpret this confidence interval? So the statistic, we're only talking about proportions. So we're talking about what's the statistic that comes from a proportion. In other words, from a sample. That's our p hat, right? So here's our formula. The statistic is p hat. And what's the standard deviation of the sample proportion? So in other words, from the previous chapter, if I have a sampling distribution for proportion, what's the standard deviation going to be? And you don't have to have this memorized. You can look this up on your formula sheet. But there you go, right? So that's going to go in here. And then what do we know about the shape of the sampling distribution for the sample proportion? Well, we hope that that shape is approximately normal. And remember, we have certain conditions that need to be met in order for that to be true, the large counts condition, but we hope that that shape is approximately normal. And so our critical values in a normal distribution, so if there's my normal distribution, and remember we said like a 95% confidence interval will go out two standard deviations from the mean. Well, that two, the number of standard deviations from the mean, is a z-score, right? And so our critical value is going to be a z-score. Now, we call this z-score, actually we call it a z-star. And the reason we call it a z-star is because, like, for example, when I say a 95% confidence interval, I go out two standard deviations from the mean. The z-score of 2, I didn't use a specific data value to calculate that z-score. So it's not a z-score that corresponds to a specific data value. It's kind of like a cutoff value. So we call it a z-star, meaning it's like our cutoff value. So there's my formula here up here in red. But there's a problem with the formula. Do I know what P is? Do I know the population proportion? No, that's what I'm trying to estimate, right? That's the whole point. I wouldn't be sampling if I knew what P was. So I need to estimate P. I need to estimate the population proportion. The best I can do is I can use P hat. So we're going to take our formula and make these two, and this is ugly. I'll show you a nicer version of this in just a second. But I'm going to make these two P's here into P hats. And so here, hopefully you can read this a little bit better, but this is our formula. This is where it comes from, I should say. So it's the statistic, p hat, plus or minus the critical value, which is a z-star, times the standard deviation of the statistic. And we call this a one sample Z interval for a population proportion because it came from one sample, in other words, one p hat. We're using like a Z star, it's a confidence interval, and we're trying to estimate a population proportion. Knowing the name is going to be helpful. And we just talked about the fact that we're not really using P. Like theoretically, this formula, if I wanted the standard deviation of the statistic, I would be using P, right? But we don't know P, so we're using P hat to estimate. And let's talk on that a little bit more. Because we're using P hat to estimate the standard deviation, we no longer really have the real standard deviation. So in other words, the real standard deviation of P hat, or in other words, sigma of P hat, is the square root of P, 1 minus P over N, right? So I'm not using that. I'm using P hat, 1 minus P hat over N. I'm hoping that these two values are going to be close to each other, but they're not going to be exactly the same. So in other words, this here is an estimate for this. And so this thing that I've circled here, we're going to call that the standard error. When the standard deviation of a statistic is estimated from data, in other words, when it uses P hat instead of P, we call it a standard error. So my formula is going to be the point estimate plus or minus the margin of error. So in other words, the statistic plus or minus the critical value times the standard error of the statistic. So notice that kind of like vocab there. We're no longer talking about the standard deviation. It's kind of the same thing. It's using the same formula, except for now I'm using P hat, so we call it standard error. All right, now let's revisit this formula here. So here's our formula. Great, we built that formula. Let's talk about it though. We know that we can only use different parts of this formula if certain conditions were met. So first of all, I need my P hat to be a number or probability that's meaningful. I need to make sure that I sample using a simple random sample or from a random, and we call this the random condition. I want to make sure that I got my data from a random sample, because otherwise, if I did like, you know, a convenience sample or something like that, I don't really have much confidence in my P hat being anywhere near my P, my population proportion value, right? So first thing, and I would say most importantly, you need to use an SRS. The second part of my formula, this Z star here, right? And we said this a couple slides ago, a couple minutes ago, but Z star is assuming that the sampling distribution is normal. How do we check to make sure with proportions that the sampling distribution is normal? We check the large counts condition. In other words, we need to check to make sure that n times p is greater than 10 and n times 1 minus p is greater than or equal to 10. Well, again, here's the problem. I don't know p, right? So you're going to notice that our large counts condition is n times p hat and n times 1 minus p hat, because I'm using p hat to kind of estimate p. It's the best I can do. So if that condition is met, we can say the sampling distribution is approximately normal. And then the third part of this formula here, remember, that's what we now call the standard error of the sampling distribution. And remember, it's the same thing as standard deviation. We're just using p hat to estimate p. We can only use that formula when the 10% condition is met if I am sampling without replacement. Remember, that's the whole idea of if I'm sampling without replacement, which anytime I do an SRS, I am sampling without replacement, that condition, that 10% condition needs to be met because of the issue of like independence. Now, we are going to talk a little bit later in the, well, I should say very later in the video about sometimes, well, what do I do if I don't use an SRS? If I do something different other than sampling. We'll talk about that in a second. But for right now, we need that 10% condition. Okay, so summarizing, here's our three conditions. You can just list them out in any particular order, doesn't matter. Data need to come from an SRS, 10% condition needs to be met, large counts condition. All right, let's talk before we go into an actual problem. How do we get the critical Z star for our confidence interval? In other words, like that cutoff Z score. So we kind of just talked about this a little bit, but if we want a 95% confidence interval, we're assuming that the distribution is normal because the large counts condition was met. So we're assuming that the sampling distribution is normal, right? This is a sampling distribution for P hat as long as the large counts condition is met. So if that's normal, you can see down here that I have Z-scores that cut off like the middle 95% of the area. I can look that up, that Z-star value, either using the table A, my standard normal table, or I can use inverse norm, or the new, and I think like easier thing that I'm going to show you is if you go to table B, and table B, this is in your formula sheet. This is a new table for us. We're going to use table B. I'm going to show you how to use this. And you can see there's a big blue X, and most of the table I have kind of like cut off. You can see I don't have the whole thing here, but there's a big blue X through most of the table because we're going to use it later, but I'm not going to go into it now. But at the bottom of table B, it says confidence level. So all my confidence levels, I'm sorry, I shouldn't say all, but a lot of the common confidence levels are listed here. So if we want a 95% confidence level, this bottom row here where it says infinity, these are all going to be, these are your Z stars, that bottom row. Those are all of your Z stars, okay? So my confidence level, 95% confidence level, my Z star is going to be 1.96. Now this table is super useful if you're doing a 90% or a 95 or 99% confidence interval. What if I ask you to do a 92% confidence interval? Well, here's the thing, 92% isn't listed, right? So now you're going to have to go back and do one of these options. Either use inverse norm, or you can use table A to find your Z star. All right, so now we have our Z star. We talked about conditions, we talked about the formula. Let's jump into a problem. So according to a 2016 Pew Research Center report, 73% of American adults have read a book in the previous 12 months. This estimate was based on a random sample of 1,520 American adults. When I read a problem like this, I'm gonna start by listing the information that's given to me. So, oh look, random sample, that's probably gonna be helpful. This is my sample size, right? So 1520 is N. And they tell me from that sample, 73% of American adults have read a book. So one of the hard parts with confidence intervals and hypothesis testing as we move forward, you're not going to be told, oh, you're going to have to do a one sample, Z interval for proportion. You're going to have to figure that out. So you have to pull out the information from the problem and say, am I talking about means? Am I talking about counts? Am I talking about proportions? In this case, 73%, remember a proportion is a fancy name for a percent. So that's a P hat because it comes from a sample. So there's the information that I need and can like jot down. All right, so are the conditions for inference met? So remember our three conditions, SRS, 10%, and large counts condition. Let's check. So they don't tell me that this was an SRS. So if it wasn't an SRS, I can't go any further. What we can do, and what I'm going to tell you to do, is that if you get a problem like this, you're going to assume that the sample was selected randomly, okay? I don't really have anything to tell me otherwise. Oh, you know what? I'm sorry. I'm correcting myself. They do tell me it's a random sample. So in this case, it's confirmed. It is a random sample. But even if it just said based on a sample of 1520 American adults, and you're asked to create a confidence interval, just say that you're going to assume it, right? Okay, so did I sample without replacement? Yes, I did an SRS, so I sampled without replacement. I need to check that 10% condition. So I can assume that the sample size of 1520 is definitely less than 10% of American adults. And now I need my large counts condition as well. So remember, I don't know P, so now I'm using N times P hat and N times 1 minus P hat. Now, one thing to note, when I plug this into my calculator, I'm actually going to get decimals. You're going to just round these decimals. If you write the decimals down here, that's totally fine. I think it was like 1,109.6 or something like that. I forget. But you can write the decimals down there, but later on in just a few minutes, you'll see what I mean. We're going to eventually have to round because we need a number of successes. All right, part B, determine the critical value Z star for a 90% confidence interval. I would look at that table B, remember? So I'm going to actually go back and show you the table. Here's the table, 90% confidence interval. So right here, that's my Z star on that bottom row, that 1.645. Or I could use my table A and find the Z score that cuts off the bottom and top 5%, or I could use inverse norm, right? So now I need to construct a 90% confidence interval for the proportion of all American adults who have read a book in the last 12 months. So I'm going to go back to that formula. So my point estimate, my P hat, plus or minus the Z star that we looked up, times the square root of P hat, 1 minus P hat over N. There's your formula. You need to write this formula down. This formula is required that you write this down. But here's the thing, who wants to type this whole mess into a calculator? I certainly don't. So you can grab your calculator, and if you go into Stat, Test, so scroll over to Test, this is going to be a new menu that we're going to use all the time. And so remember earlier, I told you we're doing, the name is going to be important. So we're doing a one sample Z interval for a proportion, right? So you're going to scroll down and find a name that matches it. Look, I see test, 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 implying that these are like hypothesis tests. Z interval, but that doesn't talk about proportions. So let me keep going. Aha, here we go. One proportion Z, it gets cut off, but one proportion Z interval. This is what we're going to use. So you're going to type in X is the number of successes. So remember, we said 73% of 1520 when I round, because you can't put a decimal in here. So when I rounded it, I got 1,110. My sample size was 1520, and my confidence level was 90%. So once I fill all that in, I can hit calculate, and it does the number crunching for me. It spits out the interval. Again, to be clear, I need to write down, let me go back in here. Your work, what work is required? It is required that you write this formula out. It is required that you tell me what the interval is. This middle step is not necessarily required. But even though you're using your calculator, you have to show your formula. All right? Now we have the confidence interval. Let's interpret it. So we're 90% confident that the interval from 0.711 to 0.749 captures the true population proportion of American adults who have read a book in the previous 12 months. And this should, I think, say, I don't know why that's a 5. So P equals the true proportion of American adults who have read a book in the previous 12 months. So keeping in mind, my confidence interval, we're talking about it capturing the proportion from the population. So make sure that your language is very clear, that you're implying that we're talking about the proportion from the population. All right, so now in this example problem, we broke it down for you. We told you, check the conditions first, right? Check the conditions, determine the Z star, construct the interval, interpret the interval. Typically, you're not going to be told all of those steps. So you need to know this four-step process. You state the parameter you're interested in, you check conditions, and then if the conditions are met, you perform the calculations using the formula, but then again, you're not doing the number crunching, you're just kind of using the functionality of the calculator. And then you always have to interpret your interval in the context of the problem. So let's see, what is this going to actually look like? All right, a recent poll of 738 randomly selected cell phone users found that 170 of the respondents admitted to walking into something or someone while talking on their cell phone. Construct and interpret a 95% confidence interval for the proportion of all cell phone users who would admit to walking into something or someone while talking on their cell phone. All right, so we have 738 people. So 170 of them said yes, they did do this. In other words, we have 170 successes. That's not an average. That's not like anything else. It's a proportion. So I have the percent of people who said yes or whatever to this survey is that, right? Okay. So what am I trying to do? I'm trying to come up with a 95% confidence interval for the true or the population proportion of all cell phone users. So not just from this one sample, of all people who use cell phones. What percent of people would admit into walking into someone or something on the phone? So it didn't tell me to, it told me to construct and interpret the interval, but I can't do any constructing or interpreting unless I check conditions. So it's not, again, I want to reiterate, you're not going to be specifically told to check conditions. You need to know that you have to do that. So my conditions, it tells me that these people were randomly selected. So because it's an SRS, we sample without replacement, we need the 10% condition. So we're going to assume that 738 is less than 10% of all cell phone users. And then the large counts condition is, remember, n times p hat and n times 1 minus p hat, but n times p hat gives you the number of successes. In this case, they specifically tell me the number of successes. So I can just say the number of successes and therefore the number of failures are both at least 10. And plug it in if you don't believe me, but plug in n times p hat. So it'll be 738, and your p hat is 170 over 738, right? So that gives you 170 there. All right, those are my conditions. Now let's get to our formula and use our calculator. So my p hat, we said, was 170 over 738, which is about 23%. So here's my formula. Again, to reiterate, this formula is absolutely required. It is required that you write that down. But then I'm not going to type that into my calculator and risk making a mistake. I'm going to go into stat, test. For me, I think it was letter A. I'm going to scroll down because this is a 1 proportion Z interval. And I have 170 successes. I have 738 as my sample size. And I want a 95% confidence interval. And so this spits out the actual interval itself. In the in the parentheses here, in the parentheses here, it gives me the interval. So I can round this to 0.2 and then to 0.26. One thing I think I forgot to mention on this particular problem is the Z star, right? We have to use the table. So I have to go back to the table. I'll go back to that real fast. I want a 95% confidence interval. So there's that 1.960. The calculator doesn't spit that out automatically when I do this 1 proportion Z interval. You either have to use inverse norm on the calculator or look it up on the table. Okay, so there's my interval. Final answer, that's my interval. Now we need to be able to interpret it. So we're 95% confident that the interval from 20% to 26% captures the actual population proportion of all cell phone users who would admit to walking into something or someone while talking on their cell phone. Okay, so that's it for one sample confidence intervals for proportions. Just a reminder, you need to do the entire process, right? And as another reminder, the margin of error only accounts for sampling variability, meaning there could be other things going on, like other sources of bias, right? Under coverage or response bias or non-response bias because of how your sampling was done initially or for whatever reasons that aren't taken into consideration using our margin of error formula here for the confidence interval. All right, so before we get in, that's it for a one sample confidence interval, but before we get into two sample, I wanna talk to you a little bit about, well, how do we pick a sample size? So when researchers or statisticians or whatever, when they plan their study, they typically set their margin of error. They say, okay, well, I want to be sure within like 3 percentage points or whatever it might be, 5 percentage points, or I want more exact data. I want more precise, let's say, data. I want my margin of error to be like plus or minus 1 percentage point. So they kind of fix their margin of error. And we know that the size of the interval, the margin of error, can be controlled by two things: the sample size and also the confidence level. So here's our formula for margin of error, right? The margin of error is the plus or minus part. It's point estimate plus or minus. Here's your formula for a confidence interval. Point estimate plus or minus the margin of error, right? And so the margin of error, or ME they use here, is that Z star times the square root of P hat 1 minus P hat over N. So what we can do is we can, if we're given like a certain margin of error, we can kind of backfill some information and solve for N. Let's look at an example. But before we do, we don't necessarily always know the value of P hat because we're selecting the sample size before we're doing the study, right? So we're going to kind of guess P hat based upon one of two methods. So if you are, for example, estimating like the proportion of people wearing red, if there have been previous studies done on the proportion of people who wear red, you could use the P hat from that previous study or from those previous studies. Or if you're totally unsure if this is the first study or if you don't want to use previous information, using 0.5 as your P hat, as a guess of P hat, is the most conservative value that you can use. So you're going to use one of those two methods, okay? And we're going to plug in either a guessed P hat or a 0.5, and then we're going to kind of back solve. So ready? Let's look at an example. A company has received complaints about its customer service. The managers intend to hire a consultant to carry out a survey of customers. Before contacting the consultant, the company president wants some idea of the sample size that she will be required to pay for. One value of interest is the proportion of customers who are satisfied with the company's customer service. So as the researcher, she decides that she wants to estimate to be within 3 percentage points. And she's fixing how wide she wants her interval to be, right? And she also is saying, and I want a 95% confidence level. So let me figure out how big of a sample do I need. So we're going to look up our Z star, remember margin of error, Z star times the standard error, right? A Z star for a 95% confidence level is this. We don't have any like back information, at least we don't know about any back information about like previous proportions of customers who are satisfied, right? So we're just going to use 0.5. That's going to give us the most like cautious estimate. So the Z star, 0.5, 1 minus 0.5 over N. And we want that to be less than or equal to 3 percentage points, so 0.03. So now, once we plug in, the rest is, we're just going to do some fun algebra. This might be the most math we do all year. So to solve for N, we can divide both sides by 1.96. We can square both sides to get rid of the square root. We can multiply both sides by N. And then let's divide both sides by that 0.03 over 1.96 squared. So you are going to have to type that whole thing into your calculator, just being very careful. And so it's telling us that your sample size, N, has to be greater than or equal to 1067.1. So notice, it's saying my sample size has to be bigger than or equal to that number. So if I use 1067, if I just round this to the nearest ones place, 1067, my margin of error is not going to be smaller than 3%. My N has to be bigger than this. So guys, you're going to always have to round up. So answer 1068. So we need to include at least 1068 customers in our sample. Got it? All right, that was all of section 8.2, which dealt with one sample confidence intervals for proportions. Let's talk about, well, what happens if I want to estimate a difference in proportions. So something like I want to estimate, I'm interested in the percent of people who like school pizza. And I want to know the difference of people, the difference in the percent of people who like school pizza at Wissahickon High School versus Upper Dublin High School, something like that. So a lot of this is going to be very repetitive to what we just talked about and to what you've talked about previously with sampling distributions as well. The conditions are the same, but now we're talking about the difference in two proportions. Here's the important part. Our data has to come from independent random samples, or, and we'll talk more on this today, from two groups in a randomized experiment. So if they're random samples, they have to be independent. Or we could have done an experiment, and remember when we design an experiment, going back to experimental design, once we have our sample and we're getting ready to run the experiment or to design the experiment, we randomly allocate the subjects into two groups, right? So that random allocation, and we talked about important reasons for that random allocation, but here's another important reason, because I need some kind of randomization. The data either come from an SRS or they were randomly assigned, right? And now let's talk more on the 10% condition. It says when sampling without replacement. Remember, the whole point of the 10% condition is because we've talked about this, you can't sample with replacement if you're doing an SRS, right? So the 10% condition is only applicable when you're sampling without replacement. And you have to check it for both samples in both and compared to both populations. We'll talk in just a second about, well, what if I'm doing like option 2 here, when I have two groups in a randomized experiment, then I'm not sampling without replacement. And we'll talk about what that looks like in just a second. Okay, and then we also need the large counts condition, but we need the large counts condition for both samples, and these should be p hats, my apologies. So this should be like p hat, p hat, p hat, p hat, because again, we don't know P1 and P2. We're estimating them with p hats, right? All right, let's talk about this formula. And remember, I would have your formula sheet out and take a look at that. We're piecing together this formula. So it's the general formula statistic plus or minus the critical value times the standard deviation of the statistic. So my statistic in this case, I'm looking for the difference in two proportions. So it's not just like a p hat. It's going to be like p hat 1 minus p hat 2, right? Our statistic is like the difference in two proportions. Our critical value we talked a lot about is going to be a z-star because we said the large counts condition is met, therefore the sampling distribution is approximately normal. Now let's get into the standard deviation of the statistic. If you remember back to the sampling distribution chapter, the difference in two proportions, this formula is kind of ugly. Here it is. So the standard deviation for the sampling distribution for the difference in two proportions is this formula here, right? But that's standard deviation. Do I know P and P1 and P2? I don't. I need to estimate them with P hat 1 and P hat 2. So I no longer call this standard deviation, I call it standard error. So it's the same exact formula, I'm just subbing in P hats. But I can no longer call this standard deviation. I can no longer call it sigma. You're going to notice that this is, I tried circling that and I kind of made it worse. I can no longer call this sigma, right? This is now standard error, SE or standard error, because I'm using P hat to estimate P. All right, so putting it all together, here's my formula. So my statistic is now not just a statistic, it's the difference between those two P hats, Z star like it always has been, and then we just talked about that standard error. All right. So I told you we'd come back to that 10% condition. So far, we focused on, producing data by a random sample. Now we're going to talk about, well, what happens if I do a randomized comparative experiment? What if I, like I said a couple minutes ago, in my design of my experiment, I am taking subjects and randomly allocating them to two groups. So take a minute and read this. Patients with lower back pain are often given non-steroidal anti-inflammatory drugs, or NSAIDs, like naproxen to help ease their pain. Researchers wondered if taking Valium along with the naproxen would affect pain relief. To find out, they recruited 112 patients with severe lower back pain and randomly assigned them to one of two treatments, naproxen and Valium or naproxen and placebo. Oh, look, now I'm talking about more about designing experiments. Remember placebo groups, placebo effect. It's important that both groups are getting two drugs. If one group is getting a naproxen and a Valium, two different drugs, the other group should as well, right? And I won't get into that whole thing, but go back and think about like the placebo effect. All right, so after 1 week, 39 of the 59 subjects who took naproxen and Valium reported reduced lower back pain compared with 43 of 55 subjects. Notice my group sizes are not necessarily the same, and that is okay. All right, so construct and interpret a 99% confidence interval for the difference in the proportion of patients like these who would report reduced lower back pain after taking naproxen and Valium versus just after taking naproxen and the placebo for a week. Did they tell me to check conditions? They did not, but before I do anything, before I construct anything, I better check those conditions, right? So we have some setup to do. Don't just go like plugging stuff into your calculator. So let's do our little setup here. And before I actually do anything, remember I always tell you, I write down like the important information. So 39 out of 57 subjects. So N1 is 57, P hat 1 is 39 out of 57, right? again, think about why are these proportions? They're proportions because I have a certain number of successes out of a total. And then I have N2, my second sample size is 55, and my second p hat is 43 out of 55, right? So you might want to take a minute, jot that down. All right, so let's come up with our confidence interval. So we're going to say that P1 is the true proportion, the population of proportion of patients like these who would report reduced lower back pain after taking both drugs. And I'm going to pause for a second. It's important to note that these are patients like these because there could be patients, they tell me that these patients have lower back pain. So, for example, if I'm a patient with upper back pain, let's say that I say, oh, you know, the Valium and the naproxen work better for the lower back pain. Well, if I'm a patient with upper back pain or with arm pain or leg pain or whatever, are these two drugs necessarily going to work the same? Not necessarily. So just to clarify, that's why we say like these. So then P2 is the true proportion of patients like these who report reduced lower back pain after taking just the naproxen and the placebo, right? So those are my two population proportions. And again, just to reiterate, read this carefully, make sure that you're clear that you're talking about what would happen in the population. So read this, for example, the true proportion, even though this person says the true proportion of patients who reported, people who reported, that implies that they were in the sample, in the p hat, right? Or in the experiment, I should say in this case. So you're kind of contradicting yourself. You're saying true proportion, that implies we're talking about like, you know, all people, but we're talking about the p hats because it's a who reported. So we don't want to say that. The true proportions of patients who would have reduced lower back pain, right? All right. Okay, now on to conditions. So random, it was not an SRS. Let's be clear, we did not do an SRS. We hope that they somehow randomly selected these subjects to begin with. We don't really know, but when they designed the experiment, they randomly assigned patients to the two groups. So that's our random condition. And because they randomly assigned patients to the two groups, we're not sampling without replacement. So we don't have to check the 10% condition. We're not sampling without replacement. So the 10% condition is not needed. If you check the 10% condition when it's not needed, you will lose credit. You have to be clear that you know what you're talking about. Because we're doing random assignment to two different groups, we don't check the 10% condition. All right, large counts condition. Again, I don't need to plug in like n times p hat, n times 1 minus p hat, because they give me number of successes. So 39, and therefore the number of failures, and 43, and therefore the number of failures are all greater than or equal to 10. So large counts condition is met. And again, why do we care about the large counts condition? That tells me that the sampling distribution for the difference in p hat 1 minus p hat 2 is going to be approximately normal. All right, now we have like the setup. Let's go to this formula, and it's going to be a little ugly. So here's my two p hats, right? P hat 1 is 39 over 57, which is 68.4%. P hat 2, 43 over 55. So I'm calculating the difference in the two p hats plus or minus the z star. Now, I just want to show you that even though this is like a two proportion problem, we find the z star exactly the same way we did before. We want a 99% confidence interval. I'm going to go back to this table. Look, 99% confidence interval is right here. My z star is 2.576. It doesn't matter whether I have a 1 sample, 2 sample, whatever. My z star is the same. Where were we? Okay, so there's my z star, and then p hat 1, 1 minus p hat 1 over n1. Don't get these mixed up. P hat 2, 1 minus p hat 2 over n2, right? So again, to reiterate, this formula is required. You must write that down. You don't necessarily have to show this middle work, because if you were to plug that into the calculator, you'd probably make a mistake. I'd probably make a mistake, I should say. I'm not going to plug that in. I'm going to go to my calculator and I'm going to go stat test. Now remember, I'm searching for an interval for proportions, but I have two proportions. So can you see option B there? A two proportion Z interval. And so my X1 is the number of successes in my sample 1 and the sample size. The number of successes and the sample size. And keeping in mind, just like previous problems, if you weren't explicitly, in this case, we were explicitly told that we had 39 successes, right? So 39, 57, easy. If in another problem, it just says 57 subjects and 20% of them, you know, experience reduced back pain. Well, you would just calculate what's 20% of 57, and then you round to the nearest whole number, okay? Confidence level, they're asking me for a 99% confidence level. So I have this all in here. I hit calculate, and it spits out the interval. So negative 0.3114 to positive 0.116. I just copy that down. Just to reiterate, the circled red here is the formula. It must be written on your paper, but then you're just going to use your calculator to come up with this final answer here. Okay, now we calculated, now we have to interpret. So look at this interpretation. We're 99% confident that the interval from negative 0.312 to positive 0.116 captures the actual difference in the true proportion, or like the population proportion of patients like these who would report reduced pain after taking naproxen and Valium versus after taking the naproxen and placebo. It's the population difference, or I should say it's the difference in the population proportions. So read that again carefully and make sure you understand, and make sure when you do your interpretation, it's clear that you're talking about the populations and not the samples. We know what happened in that one sample. We know in that one sample that there was a difference, but now we're trying to estimate the population difference, right? Okay, now part B. It says, based on your confidence interval that you just came up with, what conclusion would you make about whether taking Valium along with naproxen affects pain relief? So if I'm trying to calculate or to estimate, or, you know, capture the difference between the proportion of people who are experiencing back pain in the two groups, right? Or I guess I could have gone here. And I'm saying that that difference is somewhere between negative 31% and positive 11%. Well, think about it. If the two groups were equal, if it didn't matter if I'm taking naproxen and Valium or naproxen and placebo, the proportion of people who would improve in both groups would be the same. In other words, P1 minus P2 would be equal to 0, and like correspondingly these P hats, right? So if there wasn't a difference between the two groups, the difference would be 0. Got me? Now let's think, if P1 is better than P2, then the proportion of people who find relief in P1 would be greater than the proportion of people who find relief in P2. And therefore the difference would be greater than 0. Is this difference greater than 0? Well, we're saying here that the difference could be less than 0, but it could be positive too. It could be greater than 0. It could be 0 itself, right? And if P1 was less than P2, then P1 minus P2 would be less than 0. So when you're asked a question like this, based on the confidence interval, what conclusion would you make? We're going to decide where is that interval located. That interval is located, like, or what could be in that interval, I should say. 0 could be in that interval, negative numbers could be in that interval, or positive numbers could be in that interval. So because the interval, you know, kind of like straddles 0, we don't know. We don't know which one's better. They could both be the same. One could be better or the other could be better. We're not sure. Now, if my confidence interval went from, you know, when I calculated my confidence interval, if it went from like 0.1 to 0.5, all these values are positive. So that's an indication, oh, I shouldn't have just erased that, but that would be an indication that P1 minus P2 is always, or I think it's greater than 0. In other words, people experience more pain relief in P1. And vice versa. If it's always negative, then I could say that P2 experiences greater pain relief. So we can kind of use our confidence interval to draw a conclusion. And this is just another reminder. When my interval is just that, it's an interval. I don't know which value within the interval the population proportion is equal to, or in this case, the difference in proportions is equal to. So just like because 0 is in the interval, I don't know that the difference is actually 0. I just know that it could be 0, it could be positive, it could be negative. Remember, back to the original definition of confidence intervals, a confidence interval gives you plausible values. So any value within that range of the confidence interval is a plausible value. All right, and then that is it with 8.2. Thank you I'm sorry, that was 8.3. Thank you so much for watching.